Good morning, everyone. So, welcome to another session for the AI class, and thank you for coming to the last class of the year. Okay. First, make sure that you have all your code running. I guess you can run your code from last time. That should be fine with all the setting. Okay. And today I'm gonna actually just give you guys a little bit more theory on how the machine learning module works under the hood, especially when we are training them. Like remember, there's a function called fit, right? We're fitting our model to the data, and I guess you should at least have some general idea of like what is fit function does, and it's gonna be the same for all the machine learning model that you're gonna learn today. Okay, so we are at this page right now. That's page 30th. Okay, so last time I was saying that if you are training your model, and this one is the Perceptron, so that means that it's a linear model, right? So during the fitting, right, during the fitting, the model goes through the data like multiple times. Each time we call them one epoch, remember? And after each epoch, what's happening is that the weight is something that is kind of like a model internal parameters. So we are actually, our problem is actually to find whatever this is, W. So W is the internal parameter that we try to optimize. So essentially all the machine learning model it's the optimization problem. Okay, how do we find the weight that actually the best, right? And after each epoch, we're gonna update the weights until the weights become, I guess, it doesn't change anymore, and that's called convergence, okay? So in order for the model to know whether the weight should be updated or not, it's gotta know if there is an error first. And that error is really a big thing in all the model. Like the difference between like different model, I guess the big part of it is how do we know, like how do we quantify the error, basically. Okay, so for the perceptron, if your answer is going to be just 1 and -1, so let's keep 1 and -1. You can, I guess, rewrite this into 1 and 0 later. That's totally fine. But perceptron only do binary classification, so that means that the answer that the model is going to be given is going to give to us is just 1 and the other. Okay. So how do we know if the answer? How do we quantify that error, right? And I guess the obvious one for this is to just compare them with the actual answer, right? Because in the training data, we know the answer. We know whether the answer should be 1 or -1, right? It's binary right now, right? So why don't we just compare the one that the model predicts and the one that is the actual answer? It's called the ground truth. Okay, so that is the one right here. This is the prediction. This is the ground truth. We are subtracting them, right? If there is an error, right, this one will be, this term will be non-zero, right? If the prediction is correct, this term is going to be 0. Okay, so if you have non-zero, that means you make mistakes. The model making mistakes, right? We're going to square the term because we don't need negative number. The negative number doesn't mean anything. We just need the magnitude. That's why we squared it, right? And then we're gonna sum this error in all of the observation. So this n is the number of the training sample that we give to our model. If I were to recall correctly, actually I don't recall how many, but something along the line of like 70. I think because we have a total of 100 flowers. Remember, we having a binary problem, so I think we cut one sample away. So we have 100 sample. We split them 70, 30. So 70 become our training sample. So that means we give our model 70 observation of the flowers, and we're gonna sum the prediction that the model is giving us, and then I guess the difference between the prediction and the ground truth. Square the answer, and then sum them over the 70 observations. So that is our definition of error right here. Okay. So this error can be different in other model, but essentially you gotta have first come up with a way to quantify an error, okay? And then once we find the error, once we have the definition of error, the objective that we want to do the optimization is we want to find the weights, right, that minimize some sort of error right here, okay? So we call them J, okay, J, okay? And and I guess if I were to write them in terms of like metric notation, I can kind of come up with a way that I can write everything into like one vector notation like that. So I want to minimize this thing, the summation of that thing. That's all, right? And in order to do that, the way that we do for Perceptron, it's called gradient descent. Okay, so that one. So this one is going to be different among different models. But for this one, you can think about calculus. Like once we have the definition of error, if you want to minimize the error, you find the derivative of that error with respect to the change in the weights. Like if you change the weight, how do you change the error? And we want to go to the weight update in the direction of the decreasing error. It's like calculus again, right? Okay. So essentially what we're doing is that we're taking the derivative of this. But in the multivariable calculus, the derivative become gradient. So that's why it's called gradient descent, because we're taking the gradient of the error function, and then we are updating that weight, right? We're saying that we want to change the weight in the direction of the decreasing error. So that sign make it so that after the weight change, the error should decrease, okay? And another thing that will come into play is actually this guy right here. This guy is called the learning rate. It's eta in here, but in your code, it's eta 0, I think, okay? So that is our learning rate. So as you can see, that learning rate is nothing special. It's just the factor of which you want the weight to be changed. Okay, if eta is 1, so that means that the entire change occur from this value, right? But you can scale this value down so that the change is larger or smaller. And the way I describe this is how smart you are. Like also how quickly you are, like how quickly you can learn. If you increase this learning rate, that means your model learning things more quickly. But if you want your model to be slow learner, you can decrease this eta, okay? Something like that. And the way we visualize this is that you can think about the error. We can think about the error surface in a one-dimensional way, right? You can think about it as maybe parabola. Like usually it's more complicated than this. But if things are nice and smooth, maybe it's like parabola. And at first, you might be here. That means that the model hasn't optimized the weight yet, right? And then it's going to have a lot of errors. But once you go through this process of gradient descent, then hopefully your update is going to give you less and less error. So you are essentially moving down your error surface until you are here. So that's like a minimum. Similar things to the optimization problem. Like if you guys are familiar with that, that's the same problem. That's the same process. Okay. Okay. I'm gonna spare you some insanity, and skip this one. But if you guys wanna work it out, you can. That actually the end, the result is surprisingly simple. If you wanna calculate the weight, you can kind of work it out from calculus, and it boils down to something very, very simple. It's just like that. So it's if you want to update the weight, you just kind of do the summation over all the flowers, and then you just take the prediction and the ground truth, subtract them up, and then multiply by the input. So the math is kind of crazy, but in the end, it kind of works out surprisingly well. So that in your code, you just write something. I guess in the library code, that's all it's doing. It's just doing some subtraction, multiplication, in order to come up with the weight updates. Okay. All right. So once we have that, so this is gonna be the key to the algorithm during the fitting process. Okay. So that's what it is. So that's why I put in here. during the fitting, right, you're gonna go through this loop over and over, right? You're gonna create the error, calculate the error, calculate the weight updates, update the weight, and then redo all the error again, and then do the weight updates, right? And then every time you're gonna output the error. So that means that if I go back to this one, hopefully this loss, that makes more sense, right? This loss right here is that error function, J. If you go back here, right, remember, we have J, this guy right here. So that is a loss. And as I was saying that when you, like after every epoch, you want this loss to be lower and lower. That's the reason, right? You want, like through your gradient descent, you're expecting your loss to reduce. If it's increasing, that means that something's wrong, like either your algorithm is wrong, or actually there are some numerical instability, which I will tell you next, okay? Okay. But before we do that, okay? So normally we will actually update the weight, right? After we go through 70 flowers in our example, right? But there is another way that we can kind of speed things up. It's called stochastic gradient descent. Okay, and this name is kind of specific to the perceptron. In other model, we don't do stochastic gradient descent too, okay? But in perceptron and also in the neural network, we might do something like this. Actually, it's more complicated than that nowadays. The things that we do is that actually instead of updating the weight after 70 calculations, we just do that after every flower. And that's kind of proved to be more like a more efficient way of fitting rather than have to wait for all the flower and then kind of gather everything and do the weights update once every 70 calculations. We just do it like just once every flower. And the stochastic is just a fancy name of doing just random things. Like stochastic means random, like it's as opposed to deterministics. When you do stochastic, it means that you kind of do things in a more fussy way, a more random way. And that's exactly what we're doing here, because when you update the weights after every flower, you are introducing more randomness to the system, right? Because it depends on how, like which flower are you going to pick first. And the update is going to go in a different ways. But through this fussiness in your algorithm, it turns out that this fussiness is actually useful and will speed up your fitting process even more. So that's why it's called stochastic. So don't get bogged up by the term, but it's just meaning that people always trying to optimize things, and a lot of the technology that comes up afterward, it's just a way to make things faster, like this one, for example. Okay. So let me tell you a little bit about the learning rate, right? Because I mentioned that the learning rate is determining how slow or how fast your model is learning. And as if you just listen to me with that information, you might be wondering, like, why would I want to make my model slow learner, right? You might want to make your model fast learner, right? Because that seems to be a more efficient way of learning. And that is partially true, because yes, if your model is a fast learner, your model is going to train more efficiently. That's true. But if your model is too fast, it's gonna break down. That's called numerical instabilities, okay? So let me show you this one. This one is the learning rate of the 10 to the negative 4. So this is a slow learner, okay? And we are plotting the sum of square error. So that is the J, so that's the error function, okay? So after each epoch, right, after we go through the flower many times, you are expecting the gradient descent to work, which means that your error should decrease. And this behavior is what we want. This is good, okay? But if you increase the learning rate too much, this one, that guy right here, so the number can change depending on a lot of your parameter. But let's say this is too high in this scenario. What you're going to find out is that your error actually goes up after each epoch. So that means that your model is causing more error the more it tries to learn. So that means that it's getting more stupid in the process of learning, right? So this is wrong. So this is not what you want. So if you, so I guess I guess the lesson from this story is that you try to find the right learning rate that make your model kind of like the fastest learner without getting more stupid. Okay, so that's the moral of this story. Okay, so I guess that's kind of true, right? If you're learning things too fast, you're not learning it. You're getting more stupid, right? So you should take it down, take it slow, and actually you're learning. Okay. All right, and I guess a more visual explanation for that process of getting more stupid is actually this one right here. Right? Let me show you the way that it's supposed to do. Is that if you are learning things slowly, you are kind of nudging yourself down your error landscape so that you are arriving at this one very nicely, right? But then if you are learning things too fast, you are essentially skipping things around too drastically. And you might end up with the fact that you are having more error every time you try to learn. Okay, so that's visual ways of explaining that process. Okay, so that's why I'm saying that learning rate is probably one of the most important things that you're gonna set in Perceptron and also in neural network. It's so important because think about this, right? You know that all this language model, it takes so much time and energy to learn, and if you are setting things too small, that means you are burning your money. But if you're setting things too large, that means your model is not learning. So like finding the right learning rate is so critical in the large neural network model. This is like the first parameter that people will try to optimize. Okay. I tell you this one about this is that just for Perceptron, but then in other model, it's going to be different in terms of the cost function. The error function. Some model called cost function, but the essence, the overall theme is the same. How do we define error, and how do we minimize that error? And that difference is gonna be reflected in different type of machine learning model. So as you can see, there is no magic in machine learning or AI at all. It's just a bunch of optimization math, right? Okay. So moving on, if we can only do the binary classification, that's too limited, right? Even our toy example, there are already 3 classes, and we make it so that we only have 2. So this is not enough, right? So we want to move on to something called multi-class classification. So that means that we can now predict more than 2 classes, okay? In order to do that, actually we don't have to do anything much. Okay, we can just use our Perceptron, which can only do binary classification, but we can kind of split our multi-class problem into a bunch of binary problems. That's what we are doing. So we are splitting the multi-class classification into a lot of binary classification. So think about running things simultaneously in multiple models, right? So there are 2 techniques that we can use in order to kind of split things into multiple binary models. One is 1 versus rest and 1 versus 1. So OVR and OVO, okay? All right, so let's talk about 1 versus rest first, because I think that one is the most common, okay? This one, essentially, we're splitting things into, I guess, 1 model per class, okay? It's actually quite simple, okay? So let's say that you want to classify 3 things, red, blue, and green. So in your problem, you have 3 classes. So the normal binary classification does not work, right? But you can split this problem into 3 sub-problems that are binary in nature, okay? The first problem that you're doing is that you want a model that can distinguish between the red and the rest of your classes. That's why it's called 1 versus rest, okay? The second model, you want another Perceptron model that can separate between blue and whatever is not blue, okay? And the third model is the model that can predict green or whatever that's not green. Okay, so 3 models, okay? Okay. And you are going to train 3 models at the same time, okay? But then if you have 3 models, the next time you're giving this model, I give this problem, the new input, you're going to have 3 answers, right? Because this 3 model, once you train it, it's going to have prediction 1, prediction 2, prediction 3. So you gotta do something with the answer. You have 3 answers. How do you process this answer? So that's what's coming here, okay? So we're gonna do something called the confidence score, okay? The confidence score is kind of like an informal way of telling how confident the model is for that particular answer. And the confidence score is going to be different in different models. All the models in the machine learning can output something called confidence score. And, but the way that you interpret them can be different among different models. For example, the one that we are going to learn next is called logistic regressions. That confidence score is actually probability. But then for Perceptron and other type of model, confidence score is kind of doesn't mean anything much per se in terms of its value, but you can kind of use them to compare between different output and see if the model kind of more confident in terms of a certain particular prediction as opposed to the other ones, okay? So that's what we're gonna do here. We are going to use the confidence score, which is the Z value, okay? If you're wondering where the Z value is, let me go back to the very first page in here. The Z value, this guy right here, it's the linear combination of your input and the weights and the intercept. That's called the Z values, okay? Basically, it's like Y value in your linear equations, right? Okay? So we are going to take the Z values and we're going to treat them as the confidence score. So for example, if you have 3 answers, and for example, from model 1, right, the answer is 100, the Z value is 100. The other guys give me 10. The other model give me 50. We are going to trust this answer the most. And because this answer is telling that your flower or your sample is in the red class. So that means that we think that the overall answer, I guess the final answer should be the prediction from this model, which is the red prediction. Okay, so basically it's almost like a voting, right? Like not voting, it's like a ranking. Like you have a lot of model inside your problem, and then you're gonna choose the one with the highest ranking. So this one is almost like you're ranking the prediction, and you're choosing the first rank as the final answer, for example. Okay, so that is one versus rest, and this is probably the most common way to do multi-class. Okay. The other one is 1 versus 1. This one is a bit, I guess, higher in terms of computational expense, because as you can see that if you want to do like 4 classes, you're going to end up with 6 models. So that's a lot of computations instead of 4 models if you do 1 versus rest, okay? But this one also might be useful in certain cases. But for 1 versus 1, we're going to compare each class by another one directly. For example, if you have 4 classes, we're going to do red versus blue, right? Red versus green, red versus yellow. So it's actually red versus everything else, but separate into distinct model. And then we're going to do blue versus green, blue versus yellow, right? Because blue versus red is actually just double counting because we already have red versus blue. So we don't need that. So it's actually like this. You do red, blue, red, green, red, yellow. And then you do blue, green, blue, yellow. And you do green, yellow. That's how we choose the which match we want, right? And then we end up with 6 models. So essentially behind the scene, if you're using 1 versus 1, you're training 6 models at the same time. So that's more computational expensive, right? Instead of 4 if it's 1 versus rest, right? But this one is actually kind of nice in terms of the final answer selection because it's actually doing voting, okay? For example, if your first model predicting red, right? Your second model might predict red, the third one red, the other one green, yellow, green. essentially you are doing majority voting, which sometimes can be more robust than the one versus rest. So you might choose this one if you think your model needs a little bit more robustness, meaning that less sensitive to the change in the input. That's the definition of robustness. Okay, so you might want this one, but it's more expensive for sure. Okay, so the good thing is that you don't have to implement any of this. Everything is built into scikit-learn already. So you don't need to do anything at all. Let me show you. Okay? But you gotta know, you gotta, I guess, know what's happening, right? But you don't need to code it. So that's the beauty. Okay, so I'm gonna go to another notebook called multi-class. So we are in, I guess, S01, right? And I'm in, S01, and I'm in the C2 multi-class. Okay, so you can follow me on this example. I'm gonna retype everything again because I think that's more, that's clearer. I'm gonna close this one, and I'm just gonna create new one. So C2, IPYNB. And hopefully my Panda is working. So let me just, first I'm gonna copy. So remember this one, it's just loading the location of my utility function. So you gotta run this one first. I want, which one is it? It's always gonna select different things. Okay, so that's the one I want. Okay, I'm gonna run it. Cross my finger, and it just keep running. Okay, that's fine. I'm gonna do the things that I always do, which is to Nope. Okay, so I gotta do this again because something's not working on my computer. So let me just do that. But that's the case. And if not, I'm gonna go back to my original ways of installing Python.มี Anaconda ด้วยเหรอจริงใช้ Anaconda ก็ได้นะครับอาจจะง่ายกว่าหรือเปล่าใช้ได้ด้วยใช้ Anaconda เหรอโอเคยอมละโอเค I guess Anaconda is the best I guess it's more stable I guess my solution is the leaner but more problem so for you guys maybe Anaconda might be another way if you don't have anybody who can kind of debug things for you. Okay, what I'm doing, like which one? This one? What did I just do for the past 10 minutes? Okay, so the first thing is that I have multiple, so like my package manager install things in different places. And then in order to kind of make things work in here, there is this extension right here. So this guy needs to know where I install my Python library. And this guy actually doesn't seem to be at the right place. It doesn't detect the right installation. That's why it doesn't run. But actually my Python and everything is working, but this one doesn't work yet. And I guess that's because this one is, I guess it's built with the assumption that you install Python in a normal way. In a normal way would be like Anaconda or just installing things globally. So that's the normal way that everyone, I guess most of the people do it. But for me, I guess because I done this so many times, so I'm trying to find a way that is the quickest and the leanest. But then that's but then it's not the default way, so that's why it doesn't work with this one very well. I gotta reinstall it every time that it has some problem. That's what is happening. So I guess I'll take it back and say that Anaconda is probably your best bet right now if you are alone and you don't have the person who can figure out things for you. Anaconda would be the stable one, okay? But it's 2 gigabytes on your computer for just hello world, so that's something that I think that's ridiculous.